So, good morning. I am Krishna Kumar. So, we have discussions on what is called the Jordan term. Here we assume T is a linear transformation on V. V is n-dimensional. The characteristic polynomial of T splits into linear factors. Now, this is the important thing. Once that happens, we have already proved that T can be written as the sum of a diagonal operator and a nilpotent operator. This we have done already. So what we do is that we have, if you see the matrix representation of D, the diagonal form, then it comes, you can choose an ordered basis consisting of the eigenvectors associated with the eigenvalues, and with respect to that, D takes the diagonal form. That means there is a representing matrix with eigenvalues sitting on the diagonal, and all other entries 0. And then you see that T becomes D plus a nilpotent operator. Nilpotent operator means there is some k for which n to the power k is 0. Now, what we want to work on is how this n can be worked on, or we will go for what is called the cyclic decomposition of n, and then try to represent T in terms of the cyclic decomposition of n combined with the diagonal form of T. Okay, so let us do that. So we have T belongs to LV, V n-dimensional. Then the characteristic polynomial of T is assumed to be the product of linear factors, that is f lambda equal to dk, where lambda I is different from lambda j whenever so these are the distinct characteristic values of, so that is lambda 1 are distinct values of T. Now what one does is the following. What about the minimal polynomial? Let the minimal polynomial See, a consequence of this is that the sum of that is d1 plus d2 plus etc. dk equal to n. So let me write that also. We have the following. This is now define. Okay, we choose such that dk, right? I mean, this is not really necessary. In fact, we don't have to make this assumption at this stage at all. Later, if we want, we will make this assumption. This is somewhat redundant. Okay. Now let the minimal polynomial of t be p lambda equal to lambda minus lambda 1 to the power r1 Of course, what we have done already is that p lambda divides f lambda. They have the same factors, prime factors, and the only difference that is going to be there is in the indices of these factors. So what we have is this 1 upon 1 less than or equal to Ri less than or equal to dz. Okay. Now we know that if R1 equal to R2 equal to Rk equal to 1, T is time. In fact, it is a if and only if condition. Okay. Now, in general, f need not split into linear factors. Okay. So we are assuming that we are considering only those t for which f splits into linear factors. However, if f is algebraically closed, then f into product of linear factors. So this much we know in general. Now we are not bothered about whether f splits. Of course, we know that f splits into the product of linear factors. That may be because f is algebraically closed, or may not be because f may be algebraically closed. It depends on the nature of the linear transformation. So even when f is not algebraically closed, f may split into linear factors. This is the scenario that you have. That means f algebraically closed is only a sufficient condition for small f, that is the characteristic polynomial, to split into product of linear factors. Okay? It's not a necessary condition. This is the fact. Okay. So now what do? We define Wi equal to null space of this operator for I equal to then you know that Wi is contained in Wi, that is T is invariant, or Wi is invariant under T, and therefore, and you also have V equal to okay. Further, what you do is define Wi by that's a definition of Ti. Then what we see is that T is the direct sum of the operators Ti. Okay. So let us write down the following. The minimal polynomial of Pi is now we define the following. So let us define then what one can prove is that Ni has x to the power or lambda to the power Ri as its variable polynomial. Now what we do is, let us in fact an ordered basis. Okay, right, Wi corresponding to the cyclic decomposition for the nilpotent operator now what you have is this. See, Ti is equal to plus, this is the breakup that you have. Okay, each Ti breaks up like this. Okay, and this essentially leads to the following breakup of T. As T equal to D plus N, where D is diagonal because each of these is diagonal. Okay, so this part, if you want, you call it Di, then it is the lambda I, which is the diagonal elements of that, and it is of say Di cross Di matrix. Okay, so this is what you have. D is diagonal. D is actually lambda I taking different names for the different spaces. Okay, right? I mean, I think if you want more clarity, and probably one can write like this. Okay, so D is diagonal. Therefore, what one does is the following. We choose for Ni or we choose for Wi an ordered basis which corresponds to cyclic decomposition of the nilpotent operator Ni. That's a part. Okay. And you know that they are all going to be eigenvalues of this operator because they are all in Wi. Every vector in Wi is an eigenvector of this corresponding to the eigenvalue lambda I. So you don't have any problem there. Okay. You change that, as long as you stick to Wi, you get only the eigenvalues, and the representation that you get, no matter what ordered basis you choose for Wi, you will always get this part of the operator represented in the diagonal form. That's the important thing. Okay. Now what we look at is what is the cyclic decomposition of this is the question that we are asking. So let us start with, we will now combine this for every I later, but before that, right now we focus our attention on what is called the diagonal of the nilpotent operator. So let n and this V will be replaced by W1, W2, etc. Wk later. Okay, but we will use the generic vector space V. We assume n belongs to LV and n is nilpotent. This implies what we have is that so this means that there is some k such that n to the power k equal to 0 and n to the power k minus 1 is not equal to 0. Okay. So n nilpotent implies the minimal polynomial for n is next is lambda to the power k. For some we are taking dimension of V2 for this discussion. Okay. Now let us see what exactly is the cyclic decomposition of n. Okay. The cyclic decomposition is given by there exists vectors VR such that V is equal to VR, and the n annihilators or what you call the n annihilators of V1 VR are such that Vi plus 1 divides for I equal to so see we have got the characteristic polynomial of okay. Therefore, what you have, each Pi is of the form x lambda to the power ki, where what one gets, where k1 in fact kr is greater than or equal to, this is greater than or equal to 1. K1 is K the degree of minimal polynomial of okay. Now let me write down the companion matrix of, we are just making use of our knowledge of the matrix representation corresponding to cyclic decomposition of any operator applied to this nilpotent operator. So what do we have? The companion matrix of lambda to the power ki is the matrix that is the diagonal elements are all 0, the set of elements just below the diagonal elements are all 1, okay, and this is a so we can find an ordered basis for V in which n is the direct sum of elementary nilpotent matrices. Direct sum of nilpotent and what is this number of elements in that? Sum of R nilpotent matrices. Okay, what we have is this: the sizes of these matrices decrease increasing rank. Decreasing rank. This is what we have. Okay, and we have K1 such that K1 plus equal to N, and of course you have Ki. This is the scenario that you have. These positive integers determine the rational form of the matrix up to similarity. So what emerges is something like this. Okay? So you have this going into blocks. So this is a K1 by K1 block, and then a K2 by K2 block, KR by KR block. Okay, each one, so this is a K1 by K1. And you have all but the diagonal elements. So this is a K2 by K2 block. This is a KR by KR block. What one has is this G. Yeah. Similarly, this is the nature of the what is called the rational form of the nilpotent operator. This is how it looks like. I mean, this is the, each one is of this form. Okay. Now we Okay. So we make the following observation. The positive integer R is precisely the nullity of that means it is the dimension of null space of now we prove the following. The null space of n, that is the null space of n, has a basis consisting of r vectors given by this is the basis for the null space of n. Let us prove this. Okay, let us prove this result. So you take any V belonging to null space of okay. Then what do we know? V is, see, we take the cyclic decomposition. V is here. Okay, because each one, see, we are taking F I N belongs to is a typical element of Z ZVIN. That's why we are writing it as FIN operating over V1, etc., FRN operating over VR. What does this mean? We shall assume that Ki. That is because the n to the power Ki is equal to 0. Okay, this is because zero, that is, since lambda to the power Ki is the minimal polynomial of associated with this is the reason for that. Now our assumption is that NV equals 0. This is that V belongs to the null space of implies what you have 0 equal to NV. NV is N and you know that this is just in the same space when it's a direct sum that you have, therefore which implies n fi equal to 0 for what is the implication of that? This implies lambda times fi lambda is divisible by ki. Right? Now degree of fi is greater than ki. Therefore this implies, what do you get? Lambda fi is divisible by lambda to the power ki. Therefore degree of fi is greater than ki. This implies fi is equal to a constant times lambda to the power okay. Sorry. Ci times lambda to the power ki minus 1, so that you see lambda times Fi is Ci times lambda to the power k. Sorry. So this is the inequality. So that gives this. Okay, what does this mean? This means now you can write down. This implies V is equal to C1 n to the power K1 minus 1 V1 this is it. That is null space of but then each of this, but this is a the reason is this, that is n to the power that is the reason. Therefore, these are linearly independent vectors, and that tells that the base is this formula. Null space of n. Okay. Now we return to our original discussion. Namely, we look at what is called the now we combine with this with the result that Ti equal to on W. So dimension of Wi is dimension of Wi we have assumed is di. So that you have V equal to Wk, and n equal to this is what you have. So we now combine this with this, and what is that you obtain as a result? And we know that then Ti is in this particular form. So for each Ti comes out to be, now you see, it's, see what we are doing is the following, okay? We are working within Wi. Within Wi, every vector is an eigenvector of lambda I belonging to the eigenvalue lambda I, okay? So no matter which ordered basis you choose there, but what is crucial is we choose an appropriate ordered basis for Ni. Ni, now you see that the vector space Wi has dimension Di. Therefore, what do you get? See, what is interesting is this. Now let us look at the breakup of the Di. So what we do is we take up Wi. Wi has a breakup of the following. Z, what is called some vectors we choose for the okay. Vi1, what is the operator? Ni. This is not. What we have is that for each Ni we have a breakup. So how does that look like? So you see that Ni becomes Di. Oh, matrices of the type lambda now this is with lambda equal to lambda. Okay, so each Ni is going to be that. See how it comes up is that each Ni, see you take Wi corresponding to Ni, it has a breakup. Okay, it will, in the decreasing order you will get sort of block matrices appearing there. Okay, so therefore the matrix is called an elementary Jordan form. Matrix with characteristic value lambda. So what you have is this. See, if you take this one, this matrix, and then you can split it up. See, it breaks up like this. So what happens in this case? In this case, what happens is that if you have this form, if you have a matrix of this form, this splits up into a diagonal matrix. The diagonal matrix is lambda plus an elementary nilpotent matrix, that is okay. So this is the breakup. So this is diagonal, this is nilpotent. So essentially now we combine this. So within Wi it is going to be something like this. So within Wi the Ti is going to be, so Ti is of the form this is of this. Okay, so this is the sum of a diagonal matrix plus a nilpotent matrix. Now this is what you call the Jordan form. So this is for, so the dimension of this is essentially, what is that? You have d1, this is a di cross so what do we get? Eventually, we end up with the form. We have putting together to form a basis for V. We obtain a K where each AI di cross di, n by n matrix. So d1 plus d2 plus etc. dk equal to, how did we start? We worked with the but then each AI is of the form what about each AI? Each AI is of the form it is of the form J1I It is some n. This is what you have to do. Okay. So now what we want to prove is the uniqueness of this representation. That we shall take up in the next lecture. Thank you very much.